I will tell the audience, I made a last-minute addition this morning to our agreement where I was saying, you know, if I can demonstrate a model that'll work on a treadmill, will that be sufficient evidence, just to make sure that we have sort of a clear benchmark of what maybe sufficient evidence looks like.
Right.
And your thought is you don't want to specify that it's a treadmill.
My thought is that the agreement should specify that any model that is equivalent to the real thing is a demonstration of evidence.
Okay.
Just more general than the treadmill.
My concern is, like, what if you're like, oh, well, a treadmill is not equivalent to a tailwind, if you know what I mean.
Well, okay, so then we have to specify that it has to be a treadmill with the level to, you know, so many %. Then it has the speed fluctuations have to be below so many %. Blah, blah, blah. Okay, so if you're willing to do that research and supply this for the agreement, then we can go over that and settle on something.
Okay. I mean, if you're willing to be reasonable and accept reasonable evidence,
listen,
I'm willing to go with, like, I think what you stated is good.
We're both scientists. This is a simple mechanical problem. Okay. I'm going to solve it and present you with the solution.
Good.
I will address the purported experimental evidence, and I will be open to any forms of demonstration of this, you know, of this phenomenon.
For the audience, do you think that what the vehicle purports to do, go downwind faster than the wind, is impossible?
So, no.
You don't think it's impossible to go downwind faster than the wind in a wind-powered vehicle with no other sources of energy?
No. It's possible to go faster than the wind with the negative acceleration. It's impossible to go with a constant velocity. I mean, I'll just write down the equation. I'll show you the equation in a moment.
I like it. Yeah. With you don't think it's possible to go steady state?
Yeah, exactly.
Not possible to go steady state downwind faster than the wind.
Yeah, I mean, look, you can just throw a rock and it goes faster than the wind.
Yeah.
Right. So there's no. You know.
But a rock is not wind powered. Like the idea with the rock is it's wind powered.
Yeah, just ask your friends to design a wind powered rock, throw it in the wind, and that will do it.
You can't throw it. That's the whole point. Have you have you joined the Google Meet?
Okay. So so we have the agreement. Do you agree to make this a general statement?
Yeah. Let's do it.
So let me just mark it as resolved. Let me prepare.
Have you joined the Google Meet yet?
Oh no. So
we should do that because we're late for our.
Okay. So this was just my own Google because the other one wouldn't let me in.
Uh-oh.
So
do I need to let people in?
I don't know. No, you actually didn't set up.
Professor Kusenko, greetings.
We should get the pronunciation right.
Yeah. So no, it's Kusenko, but it's actually Alex. It's just Alex.
Okay.
So I suppose we just.
Alex.
Yeah. Very nice to meet you, Neil. Very nice to meet you, Bill.
But are you a sailor? Is that a true?
Yeah. Actually, that's true. In fact, I do sail. You know, definitely more than 1,000 miles every year. But we do it in different parts of the world. In French Polynesia, every year we go to French Polynesia in September and sail the equivalent of a distance of between Los Angeles and Vancouver. And we also sail in other parts of the world. You know, I charter a boat. My wife and I are sailors. We really love that. And here in California, we go sailing.
As a sailing physicist, it meant you're highly invested in your arguments here.
No, not really, because well, look, okay. This argument that I will present simply shows why the sailboat that I sail only has sails and doesn't have a propeller connected to some contraption connected to something underwater. Okay. Otherwise,
Before we get into this discussion, maybe should we sign the document?
Yeah, I think that's better, right? Because that's right. Because if one of us just realizes, oh, I am wrong, okay. So let's not give any hints to anyone. I mean, no. Okay. So for the record, I was actually reluctant to accept this because normally I wouldn't charge money to explain a problem on mechanics. But as the agreement stipulates, the money will go to Kudu, which provides, it will support building affordable, high-quality learning materials that are available on kudu.com. And so that is where Derek's money is going to go. So that's why I feel comfortable accepting.
You feel
accepting
good about
the,
this.
Yeah, exactly.
All
Accepting
right.
the money.
And in the case that
Just a reminder,
if I win, the money will go somewhere reasonable. Maybe back to the original creators of Blackbird, because they don't.
I mean, actually, I'm a great fan of Veritasium. So if there was a possibility that Derek would make money off of this, I would be happy because it would go to making good videos, explaining science.
Usually good. Usually,
Right, exactly.
usually correct.
Exactly. Look. No one is perfect, but you have a much lower error rate than most people on YouTube in YouTube space. I mean, there are other people who do science on YouTube. There are other people who do physics on YouTube. I will not mention any names, but I admire your work because you really are, like almost error free. That is remarkable, right? When I walk into a classroom to teach a class, I want to be error free, okay? But I slip sometimes, right? And so it's an extremely valuable skill to be able to do it at that level of quality as you have done over the years.
Well, I appreciate you saying, and also, I'm excited about this bet because if I am wrong, then I want to know. The whole point of the channel is to get to the truth, and that is, I think, why we're all here today. And I think, this is a great chance to sort of see, let the ideas win out.
That's right.
Yes.
Okay, very good.
Shall we sign?
Yeah, exactly. So let's do the signing. So we, grab a pen, and we sign. All right, so
Should we sign simultaneously?
Oh yeah, why not?
This one, Mike?
All right.
We're witnessing. Neil and I are witnessing. Is that
Yes.
right?
Yes.
We're witnessing an election.
Yeah. So here's the agreement. On
Well, we could send you a link to it.
yeah. Okay.
Wow, there's some paperwork there.
Yeah. Exactly. It's
Neil, have you examined this document?
no, I haven't, but does it matter if we're only simply witnessing their signature?
that is true.
Yeah.
That is
And
true.
we'll send it to you once it's signed.
Yeah.
so-
Absolutely. You'll get a copy in a minute.
Sure.
Okay. So shall we?
Yeah.
Brother
Ready?
Neil, it's good to see you.
Yeah,
All right, here we go.
too long.
Oh, maybe it can only take one
yeah,
at a time.
It can take only one at a time because it's this low latency. Okay. So
Okay.
Well, that could be by design, kids.
okay.
It could be intentional.
Very good.
All right. So now let me demonstrate.
Witnessed.
Yes. Thank you. Thank you.
Witness,
So
yeah.
so the agreement has been signed.
All right.
All right.
I guess that's Derek's signature.
That's my
I guess.
scribble. You know
Yeah.
what? I bought a house here in LA, and because you have a middle name, they wanted to see the middle name in the signature. So I ended up having to write out this long thing, I don't know, a billion times on a piece of paper, and I resolved that day that from now on it'll be an indecipherable squiggle, so no one can claim that the middle name is there or not there. So anyway, true story.
So he signed his signature a dozen times, and it just about killed him.
No, it was many. It was like, how many times you have to sign? You have to sign 50 things. It's a pain in the butt.
Yeah.
And Alex, I just want to say, I agree with everything you said about Veritasium, that generally I can watch it and not have to wonder, is he going to mess up? How am I going to...
No, he's brilliant. No, it's brilliant.
But
all that aside, can
Right.
a boat go downwind, or rather, can a vehicle go downwind faster than the wind?
make finish complimenting the guy. So all I'm saying is that what I enjoy about it is I don't generally, almost in every case, I don't have to think about the physics. I can think about your methods and tools of teaching the physics, which has great value in this entire enterprise that we're all a part of. So it frees me up to say, wow, that was good. Well, he walked that route. That was good. Well, that was a camera angle. That was good. And so thank you, Derek, thank you for your service.
It's my pleasure, and thank you for watching, and thank you for saying. So, Alex, you have a presentation for us now.
Yeah, so I have put together a few slides. It's a sloppy presentation, right? Because I actually didn't get a chance to do this until yesterday. The first time I watched your video in its entirety was actually yesterday. So
this is a good admission.
Yeah, because I have a broken humerus bone, and I'm doing physical therapy and everything. So it's just. Plus the work, plus everything. So it's a little crazy. Anyway, so I'm going to make a short presentation. and explain. Let me see. Okay, let me. So first, well, I assume that you have seen the video.
Okay. Is that the claim?
Yeah.
Sailing or a vehicle?
Oh, okay.
Semantics, but I think it's the same claim.
Okay.
Sort of semantics. Go ahead.
Bill, that's a very good point. Okay, Bill, very good point. So in the agreement, we took the, we carefully worded what the claim is, and I think that agreement is unambiguous. My presentation, which I put together yesterday, will have ambiguities. Okay, so I apologize about that. All right. So what you see in the video, let me start with, physics is an experimental science, okay? And the first question you may ask is, why am I not believing the experiment, okay? So let me first explain what I see in the video. In the video, the vehicle is operated in a gusty wind, and what is happening is, let's suppose this vehicle can go 70% of the speed of the wind, which is challenging. But let's suppose it can go to up to 70% of the speed of the wind.
So the speed of the wind, the 70% number is as a bluff body?
Yeah. Okay, look, again, I will not be very careful with my words, okay? But let me just finish that sentence. So let's suppose the wind is sailing below the speed of the wind. And then the wind goes down. So then what happens then? Then the vehicle for a while will be sailing by inertia faster than the wind, right? And so in this picture here, you can see the point. Initially, you have the wind speed exceeding the car speed, but then the wind speed is not constant. The wind speed drops, and the car moves by inertia with deceleration for a while until it reaches the same sort of ratio below the wind speed below. Okay, so what is needed to explain the phenomenon shown in the video is just the gusty wind. Okay, the vehicle doesn't have to have the ability to move with a constant velocity faster than the wind. But of course, there is no reason why it cannot move faster than the wind with a negative acceleration. In fact, that will be my conclusion at the end of this presentation, that whenever you have velocity faster than the wind, I'll actually show you in an equation, the acceleration is negative. Okay? The second effect that, in my opinion, is smaller, but I don't know. The second effect is that the wind in the video is measured at the height of about a meter or meter and a half, above the ground. But the propeller goes to some 3 meters above the ground. If you look at the distribution of speeds, actually there is an equation that you can write and everything. So I plugged in some numbers, and I believe that the wind speed difference between these two heights should be about 10–15%. So the vehicle could be moving faster than the speed at 1 meter, but slower than the speed at 3 meters. Okay. Now I think that this is a small effect, and in order for this effect alone to explain the observation, the vehicle would have to be moving something like 80 or 90% of the speed of the wind to begin with, which I think is very challenging. Okay. However, in combination with the previous effect, it just can make this more frequent, right? I mean, gusty changes in wind by factor 2 are very common, but here you don't have to even go to factor 2. You'll have to go to factor 1.8. Right?
And for the record, I'm willing to accept and concede the wind shear point that the wind is faster at the location of the propeller than at 1 meter.
Oh, what about your opinion on the gusting? Are you willing to admit that the wind changes velocity with time?
Is the wind gusting in time? Yes. I still think, I guess, I don't know if you want me to make a counter-argument, but
it's up to you.
My counter-proposal would be to you that, if it depended on gusty winds and things rising and falling just at the right time, that doesn't feel consistent with my experience of being in the car.
Mm-hmm. Okay, very good.
Yeah.
So I will echo.
let me ask another. Am I allowed to ask questions?
Let me just quickly respond to this because
I'll
Derek.
take notes.
Yeah, no, I'll give the mic to you in a moment. So Derek just said that gusty wind is not something that he experiences in the car.
No, it's not that it's not what I didn't experience. It's that like if the functioning of the craft were reliant on this gust effect,
right,
and it has to happen just at the right time, because that car takes a while to come up to speed, and then it takes a while to brake and all that sort of stuff.
Right.
If there was a significant gust effect, I would expect to see more unreliability, like we would do more runs where it's hard to get over the speed of the wind, or the telltale would be dancing around and stuff like that, which is not what was observed. Anyway.
All right. So I was just going to say that my experience, I mean, actually, don't drive that much. I walk to work. But my experience comes from sailing, and I see gusty winds all the time. And I sail in gusty winds. So in my opinion, I mean, wind is a thing that is like a living thing. It changes the velocity in the frame of the boat. The change of velocity corresponds to the change in direction. So you have to adjust. You have to trim the sails in response to the changes in the wind velocity. So in my experience, the wind speed changes all the time.
Okay.
Now, Bill.
Note here, if I can, that I think, Alex, nothing you have said thus far is controversial. Whatever is going on those salt flats, it would include everything you just said. So this is a foundational description of things that can happen and would happen to the craft. There's nothing, right? So we agree. So the real issue here is the craft is claimed to be doing something more than this.
Right.
And so I want to assure myself that I understand
Right.
where the points of conflict are.
Right.
No,
The craft
is denying anything you're saying now.
Right. The craft is claiming to do what my red line is showing, with the red line being horizontal. Okay. Bill. Right. Bill, I'm sorry I interrupted you. So please, what was your question or comment?
Well, are we also taking into account the model on the treadmill? The
Very
model
good.
on the treadmill is not subject to gusty conditions.
Okay.
Also, I think the model on the treadmill has very little, you use the word shear, which is understandable, but I think what you meant was gradient. A gradient of wind speed between the
I think I
surface
used the
and
word gradient,
radius.
and Derek used the word shear.
Yeah, it's my
I
bad.
say, so
My bad,
just-
Bill.
No. So just all good, but we're talking about a gradient. The reason you build a tall ship is to get your sails as high above the sea surface as possible. But
That's
I
right.
think in the treadmill model, that gradient's probably very small.
Absolutely.
Now I'll give you that in the treadmill model, the wind, the air coming out of the fan may have its own vorticity, its own spin, which may influence the efficacy or the push from the propeller, where if it's countering, if it's spin versus spin. But I think, let me say, I'm hopeful that we will explain or reckon both the Blackbird craft on the desert floor and the model on the treadmill.
Thank
Over to
you. Which brings me to my next slide, problems with the treadmill experiments. And so on this slide, you can see a list of problems. First of all, with that little hydraulic level, it's very difficult to adjust the level to the few percent accuracy that you would need to conduct this experiment. Moreover, the level is it's attached to the frame of the treadmill, and the belt is doing something else. Right? The belt can be at a different angle. The belt doesn't even have to be a flat surface, because belts tend to sag between the supports. And also importantly, the speed of the treadmill fluctuates. I actually pulled out the data, and I give you the source, for the fluctuations of treadmill speeds. And you can see that they are non-negligible. Now, what is happening here is that you spin up the propeller in that light model. You spin up the propeller at higher speed, then you slow it down, and then it uses the kinetic energy to advance. So there's a lot going on there. If you have a not perfectly flat belt, if it bulges, and if you have speed variations, then it can also go up and down. You can actually have waves going on the belt, right? But another important and interesting element, which I actually would like to understand deeper, is the effect of the human sort of steering. Okay, so if you have this fluctuating speed of the treadmill, and the human doing this thing with the spork, then the effect of inertia of the propeller creates what is called window function, and it averages the fluctuations over the window function. So it creates this weird thing that you will be kind of going forward and then going backwards, not at on the time scales of the fluctuations, but on the broader time scales. And then if a human just sort of steers it, it then can introduce unconsciously a bias towards the desired result, because you kind of hold it down when it goes down, then you relax, and then there is a period of time when it marches forward. So all of that is not the evidence against it. It's just a statement that there's no evidence. So in principle, I can imagine a very carefully done experiment on a treadmill that is built for that purpose, that doesn't sag, doesn't have waves on the belt, doesn't have large fluctuations in velocity, right? So I can imagine it being done, and but I haven't seen any experiments of that kind. Therefore, I will have to resort to theoretical arguments.
Okay.
And as a theorist, I'm happy to do that. So the first theoretical argument is actually present in the video. It's this argument of energy, and it's this beautifully done animation that shows that there is this area behind the craft that has smaller velocities than the rest of the wind. Okay, and the conclusion is that wind loses some energy. Now this is true. In fact, even if you just normally sail downwind at lower velocity, the wind still loses energy. The wind always loses energy. That's the thing about the wind. It never wins. Okay, it always loses. But the thing is, how much? And where does that energy go? Okay? And here the energy is applied to the blades of the propeller, which through some mechanical contraption are connected to the wheels. And this work is the work that contributes to the work of total friction, right? So this adds to the work of the friction. And so it actually works to slow down the craft and create that negative acceleration that I am promising you to write in an equation. Okay, so, but these are all sort of hand-waving arguments, right? Let's go and look for some real physics. Okay, somebody has to write equations. All right. So I did this yesterday. So I didn't examine all the sources. I examined two sources. One source was recommended by Derek, and that is a video presentation by Rick Cavallaro. And Derek specifically told me to look at that interval of 5 minutes. And the other one was a Wikipedia article, which cites several papers. So I looked up that paper, which in my slides is reference 1, and it turns out it's the same argument that is presented in the video presentation. So I decided I would just stick with that argument, and then if there are any other arguments, we can address them, because after I address this argument, I will present you my own solution to this mechanical problem. Okay. All right. So this is a snapshot from the paper, which again presents the same argument as presented in the video, and it has this notation which is not necessarily my favorite, but this V is car speed, W is the wind speed, FP I also dub it thrust, T thrust, and then FT for some reason is friction or drag, and etas are all efficiencies, and they're just numbers between 0 and 1. Okay. So the argument goes like this. Okay, so we have this craft that is rolling on the ground, and the wheels push the propeller, and the propeller pushes the air. So let's compare the energy that is inputted into the system with the energy that comes out of the system. And since it's rate per time, we're comparing powers. So the energy that goes into the system is this F friction times the velocity. And that's just because the craft, the work is force times distance. You differentiate with respect to time, you get force times velocity. Done. Okay? Then you multiply by eta, which is an efficiency, which is a number less than 1, but that's a different story. And then we say, where does this energy go? Well, it goes into the work done on what? Oh, well, so they write that there is a power disseminated by the propeller. And they write that power as the relative speed of the vehicle and the wind times the thrust. Okay? Now, the problem with that argument is that, and then in the calculation, there's a sample calculation in the video where they take a small difference in velocity, like 5 miles per hour difference. And so what happens is that the first term has big velocity, and the second term has a small velocity. And they say one force times velocity has to equal the other times force velocity. And the smaller that force, the smaller that velocity is, the bigger is the force. And so that is the equation that Derek is testing, risking his life. And now, now here's the real danger, because if Derek drives very close to the wind, that difference in speed goes to 0, and then this force goes up. If that difference in speed is not 5 miles per hour, if it's 1 mile per hour, then it's a huge force. If it's 1/1,000,000th of a 1%, that's like a nuclear bomb exploding behind him. Then Rick is definitely in trouble. Derek is definitely in trouble, right? So we need to find something to save Derek's life here. This is serious, right? Good. Because by division by 0, these people produce infinite force. When nothing actually should be happening, because you're just moving at the speed close to the speed of light. Speed of wind. Yeah, speed of the wind. Yes.
Good. Okay, so I want to know how my life is saved.
Right.
What is the solution?
That's right.
Here?
That's right. So let's save this life. So first, I will start with a hint. Okay. So let's forget about this mechanical, complicated system and just look at the rocket. So when the rocket flies, there is source of energy, and that energy goes somewhere. Where does it go? Well, it goes into pushing air and into pushing rocket. Right? There are two pieces. Right? You have to. There's work done by accelerating air, and there is work done by pushing the rocket. Right? So if you forgot one of those pieces, you'll be missing some energy. Right? Now, if a shell explodes into two pieces, you have to count both pieces. So that equation should have two pieces. Okay? So why is it? Why is it just one piece in this equation? And which one? So I'll show you the piece that is missing, and I'll show you that this piece is actually neither of those. In fact, it's just an incorrect piece. All right, so now let's go to correct physics. So we have some energy that is collected by the wheels, transmitted to the propeller, and now that energy is, forget how it came to be, that energy is being used to push the craft and push the air. Okay, so that energy can be calculated as in my equation here, which is just the thrust times velocity. That's the energy going in. That's the amount. But now we have to calculate what happens next. Now, it's actually not so straightforward, but okay, so you have this propeller, and this propeller has to have actually two speeds. The propeller cannot operate or cannot dispose of any energy if the speed of air coming in equals the speed of air coming out, and Derek knows that. In fact, that was part of his explanation in that animation. So there are two speeds, W1 and W2. Okay, that's why I have two speeds instead of W in that paper that I presented earlier. Okay, and I'm just trying to use the notation close to that paper. So there are two speeds, and you have to compare the energy of the air coming in with the energy of the air coming out, and that is mv squared over 2, right? mw squared over 2. But of course, m is something that's being fed, and so if you go through the equations, you will arrive at this equation here, that the power distributed to the airflow is m dot times w2 squared minus w1 squared over 2. So the w squared over 2 is just kinetic energy, and m dot is the rate at which the air mass is coming in. Now, you can also consider momentum conservation. The momentum that you give to the air is the thrust, right? That's the rate of momentum to the air is the thrust. So you write this equation for the thrust. That thrust is equal this. Again, comparing, again, there's this m dot, which is the rate of delivery of air, and there's a difference between the two velocities. So I don't know what m dot is, but I can eliminate it from these two equations, right? Because this difference squares, I can write it as the difference times the sum, and, or, you know, hooray, I have something that looks like a thrust. So I can write the power disposed in the air as thrust times the average of the two velocities, the wind coming in, wind coming out. Okay? And I give the source to someone's lectures from MIT where this is explained. But again, this is not a careful presentation, so it's just a random source, and I copied the link so you can. But I mean, this is an old textbook, right? I mean, you don't even need the textbook. This is something my students in Physics 1 can work it. All right. So now we have all the pieces. Let's write down the equation. So the power coming in is the friction force times the velocity, multiplied by the efficiency factor, because efficiency is what, that mechanical contraption transmits it with imperfect efficiency. This is equal to the sum of the air and the car powers. And you probably want to point to the equations, because that's where all the action is.
Good.
All right. So the power coming in equals the power going out. And this is the work on the air plus the work on the craft. All right? So now we have an equation that allows us to relate the thrust, Fp, and the friction force, which is now total friction, including everything. Right? So we manipulate this equation. The thrust is now the eta times friction times this ratio of velocities. And I apologize that I switched from big V that the paper used to little v, which my hands tend to type for velocities. All right? So this expression is always less than 1. Right? Because you take 1 and you divide it by 1 plus something positive. Right? So this expression is always smaller than 1. That means that the thrust is always smaller than friction times efficiency, and that in turn is smaller than friction. Now it's time to write Newton's second law. The acceleration of our craft is the sum of all forces divided by the mass of the craft. So the sum of all forces includes the thrust minus friction, and that is a negative quantity because thrust is smaller than friction. And then it has also all sorts of air drag, which subtracts another amount from this. And that tells me that this whole sum, when I divide it by a positive number m, is less than 0. So this equation tells me that the acceleration of this craft is negative. So when so it's possible to move the craft faster than the wind, but it's not possible to move it at 0 acceleration, which would be needed to maintain constant speed. Okay? So that is my solution to this problem. Okay? However, I am sort of curious where that expression came from. So I have this other slide, which is an attempt at forensic exploration of where the incorrect expression came from. And I spent a good 20 minutes yesterday poking around the internet and Googling thrust, propeller, etc. And what I found creates a hypothesis. This is not a scientific hypothesis. This is a social hypothesis by an amateur social scientist. So this hypothesis is that when most propellers are attached to planes that fly faster than wind, and they don't care about the wind. And so this W1 and W2 are close to each other compared to the speed of flight, and their average is close enough to the speed of flight. So what you find in many reference books for propeller efficiency is that the useful work by the propeller is equal to thrust times the flying speed. The useful work is only one of those two pieces, but that's okay, right? Because then they divide by power that is produced by the engine, and they get efficiency, etc. But this expression that propeller's power equals thrust times velocity is used very frequently. Now it could be that someone misinterpreted that and said, okay, so if the flying speed is speed in the air, that maybe we should take relative speed to the wind, okay? And and then we use thrust times that difference in speed as the propeller power. Right? And I'm just speculating here. Basically, this approximation of W1 plus W2 over 2 by the flying speed is valid when V is much greater than W, either of those W's. But maybe someone subconsciously extrapolated or without thinking extrapolated that approximation to the regime where V is close to the speed of the wind, and then just used it incorrectly. Okay? Maybe. I don't know. I have no idea where that expression comes from. One thing I know is that if large velocity rises from division by 0, then something must have gone wrong. Okay, and I was just trying to analyze what went wrong. And this concludes my argument. I believe that the experiment in the Veritasium video is consistent with the car's behavior expected in a time-dependent wind. And time-dependent wind is consistent with all my sailors' experiences. And the experiment does not prove the possibility of a wind power sustained sailing dead downwind because it's just a snapshot at the time when I believe it is decelerating and the wind has subsided. So it's just there's nothing wrong with the video we're seeing. It's just the speed of the wind is not constant. That is my understanding of that video. There are other effects such as gradient of the wind speed that can be a contributing factor. For that gradient of the speed to be the leading explanation, the craft would have to be moving close to the wind speed to begin with. It would have to be more like 80% of the wind speed, which I think is challenging. In a sailboat, it would be hard. Anyway, so now there are incorrect theoretical arguments that I found in the literature, and I haven't found any correct arguments. Okay, now. There could be other incorrect arguments, right? So I decided to I'll sit down and just solve that mechanical problem, and I presented you with the solution. And the correct solution shows that whenever the craft is moving faster than the wind, the acceleration is negative. So it's consistent with what we see in the video. It is consistent with the laws of nature. There are no singularities. There is no infinite force arising from division by 0. That is a good description. Now, it's good description. It's not a complete description. Why? Well, we're dealing with air, right? So to do a full job, you'd have to consider the fact that the pressure in front and the pressure behind the craft may be slightly different. And there is also an additional contribution of delta P, the difference in pressure, times the effective area, blah, 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 okay? Now, that is dealt with in textbooks on aerodynamics. That effect is generally small, and I'll tell you why it is small. Because, you can actually identify a volume that sort of follows the flow of air and is not so sensitive to pressure differences. So it's complex, but it's small. Okay. So there are other effects. There's turbulence. There is dissipation, just because every time the propeller slaps air, there is dissipation of energy. The air, So this there are all sorts of other effects, but these effects, in my opinion, are small compared to the effect I described in my solution. Okay, and that concludes.
If I remember the video correctly, Derek reports that, or the owner of the craft, of the Blackbird, reports that they've achieved up to 2.8 times wind speed. That feels much higher than what is possible here, unless the wind had picked up and then spontaneously sort of dropped to near zero.
Very, very good question. Okay, so I think today around Channel Islands, the wind speeds are like between 10, according to the forecast, between 10 and 20 knots. Okay, and so the gusty wind by factor 2 is actually a common occurrence. Now, in order to go 2.8 times the speed of the wind, you will need a gust of factor 3, not 2, right? However, if you're going for the record, you probably will do many attempts. You will be sampling that gusty wind over and over and over until you set the record, right? That's how you set the record. And on one of those occasions, you will get a nice strong gust, which is 3 times the ebb that comes after it, okay? And that's when you will clock the record, and that's where that 2.8 factor will come in.
And so it seems to me all we would need here is a wind speed monitor right in front of the propeller and a wind speed monitor at the nose. So that'll get you whether there's a gradient. We'll get to understand that. And we need an accelerometer so that when you do hit those top speeds, in that instant, that you don't just keep going more or faster, that it always has to drop.
Neil, this is a very good idea for a very good experiment. And coming from a great scientist, that's what it is, right? So obviously, I agree that if you measure the wind speed and record it as a function of time, and if you measure the acceleration of the craft and record it as a function of time, and if you do it, also take into account the speed gradient, you will get a reliable experiment. And assuming that the errors are small, you'll be able to discern that behavior which is on the screen. Okay, so I think this is
accelerometer is the key. If you had an accelerometer in the forward aft axis, you get there very quickly.
Very quickly.
Yeah.
And Derek, didn't you have a smartphone? Don't those have accelerometers?
You say it.
You have
Well,
it.
not just that. There are apps that would get you there. But let me ask you a couple things. First of all, you went through the equations very quickly. I'm not sure we have taken into account the.
Do you want to go to the equations?
The mass. You had the rate, the mass going through. First of all, dividing by 0 is clearly screwed up. I mean, there's trouble there.
I'm glad we agree on that. I'm glad we agree on that.
What's throwing me off was interchanging W's and V's. You went through it. You've thought about it. I'm just catching up. But the mass m dot on fore and aft of the propeller's got to be the same.
Right.
The area that's of the wind that starts on the low speed side is going to be bigger than the area of the wind on the downstream side of the propeller, and the downstream side is the upwind side of the craft.
Yeah, very good.
I just want to think that through.
Yeah, no, absolutely.
Just running a test.
Why is the area different?
No, absolutely.
Because the wind's going faster on the high pressure side of the propeller.
Absolutely.
It's a helicopter.
Absolutely, that's right.
I mean, I'm thinking out loud.
No, so the source I provided discusses all that. Bill is right on the money. Okay, so this is absolutely what needs to be taken into account, and that's why I provided that source. If you click on I'll provide you with my presentation, and if you
that equation down there at the bottom is very familiar to me.
Yeah, absolutely.
And you see, they're using lowercase u. W's, D's, and I'm thinking as fast as I can here.
Yeah. I mean, look, this I just copied it.
Did you just talk about conservation of mass? That's all that's going on.
Yeah. Yes.
Yeah.
Yes.
Well, which is not irrelevant because
but
it's got to be conserved. But so let me ask us this: experimentally.
No, but let me just to finish.
Can we all look at the treadmill video together? You follow what I'm saying? So what it may be that the guy with the spork is inducing the model craft to go across the wind now and then. As you pointed out, Alex, going downhill now and then.
Yeah, I'm 100% sure that the guy in the video doesn't do it on purpose. Okay?
Yeah.
However, if he is expecting forward drift.
Yeah. Oh, it's classic.
Right? Yeah, absolutely. That's what exactly. Okay, so you got it. You got it. Yeah, it's a classic way that people confuse themselves while doing experiments in an unpredictable, uncontrolled environment. Okay, and that environment is totally uncontrolled because you don't have control over the shape of the belt, over the speed fluctuations, which induce bulging and waves on the belt. You just don't have any control in that experiment. And then you introduce conscious observer. Who I'll tell you a story. Okay, I grew up in the Soviet Union. But it's a nice story. No, it's a nice story. It's a nice story. So I grew up in the Soviet Union, and so one of the old professors in Moscow State University told me this story that in the 30s there was an experiment at Moscow State University which discovered equilateral series of levels in an atom. Not like Rydberg or anything, right? Equilateral series of energy levels. Crazy, right? How did they discover that? Well, they did the measurements, and then they recorded the measurements, but then they checked the power, because in Moscow in those days the power outlets produced something that fluctuated wildly. And when they were happy with the result, they would just record it. And when they were unhappy with the result, they would check the power and say, oh no, it's not, the power is not correct. So they would cross it out, right? And that led to this very convincing set of data, okay? So I think that there's so many ways in which a human being can bias the result of the experiment by fiddling with the spork on a treadmill where there's no control of fluctuations and errors, okay? So I would be curious to figure it out, but I'm not prepared to make any claim. The claim that I would be certainly happy to make is that the people doing that are not lying, okay? They're not trying to deceive anybody. But they may be doing something that don't realize they're doing, okay?
And you make a very good point, Alex, about repeating the experiment until you have your own personal best record. And then that becomes the record, and you get to report that when you're really sampling wind variation and finding the one that actually gives you that much gradient or that much variation, and then presenting that as the new fun physics. I'd recommend here that that this experiment get conducted. I don't know how often they drag the craft out onto the salt flats, but if you load it up with some accelerometers, I think that'll settle everything here. And Alex, everything you present is quite convincing on paper, and especially landing on Newton's laws. That was classy.
I get paid to do this not only when I bet, but when I come to work every day.
That's true. It's not an optional thing.
Exactly.
So I have a question though. Could we take the model, the toy, to a bowling alley, to a place like that, where you have a run and the airspeed, but maybe it's not worth doing. The accelerometer is going to do it. But dividing by zero, come on, you guys. I never looked at that. I was at Sci-Fu camp when these guys did this presentation, and I thought, that's pretty cool. Now, as a sailor, can you do a velocity made good downwind faster than the wind?
I can do it at close haul.
You can do a velocity made good downwind faster than the wind.
Okay, it depends on the boat. The boats that I can afford usually cannot do that. I don't own a boat. I charter boats, and the boats that I sail wouldn't be able to do that. But there are better boats, faster boats.
Those boats have outboard motors.
No. I'm talking about just the sailboats, okay? And right, so I will not, when I go to Channel Islands, I will not be able to demonstrate it in a boat that I have access to. However, I could demonstrate it if you get me a better boat. I can even arrange for a better boat, but it will have to be funded by someone other than me.
Got it.
So how would you explain that? In other words, I'm not talking about absolute speed. I'm talking about getting downwind faster than a guy with a
balloon
spinnaker.
And in fact, that was shown in one of the video animations with a person
on the cylindrical Earth.
Faster than a balloon would that's traveling with the air. And
I remember living in Seattle, there were people who raced boats, and they talked about when you try to tack that much, you lose time against the guys with spinnakers.
Yes.
And this good friend of mine is at Cornell. They have all these rules about not using the rudder to scull to give yourself a push, and the lightnings, that smaller boat.
Yeah. So
you got me thinking. But man, your argument, Alex, is outstanding.
Thank you. Just to address your friends from Seattle, they are correct because they take into account their, the design of their boats. Okay, so to get sailing that fast. If you take, I don't know, Benito 45 foot that I usually sail, it's just, it's a comfortable boat, it's a fast enough boat, but it doesn't go much faster than the wind in any conditions, right? So, and to go faster than the wind when your velocity is multiplied by cosine of the angle, it's even harder. So it's just, but you can, there's no law of physics that prevents you from designing a boat that will do that. And in fact, boats are available that do that. Now,
they do velocity made good better than the wind?
yeah, I mean, look, what you need is high speed.
An outboard motor.
No, well, okay, very good. Okay, no, right. But let us. So we agree on the outboard motor. Now let's replace the outboard motor with a huge sail. Okay, so the boat I sail every year in French Polynesia has a huge, two huge sails. It's a 55-foot catamaran with two huge sails, 100 square meters, right? And in that boat, I can do, I can do 12 knots if there are no waves. I can do 12 knots in a 15 knots wind, but it still is not, that impressive to you, right? Because catamarans don't sail very close to the wind. So let's do a monohull, and let's make that huge, gigantic sail, right? The more the sail, the stronger is the force, the faster you're going to go. Now, you also need the shape of the boat to be good and everything, right? But basically, to get in that regime, you just need more force, and that is provided by more sail, okay? Now, most boats, you just don't have the place to put a big enough sail for that task. But people have built racing boats that have unbelievable, sail to volume ratio, and with those fast boats, you can accomplish what you want to do here.
You can do a velocity.
Yes.
You can do a velocity made good.
Yeah, because that velocity is just a function of the sail up to the point, reaching the whole speed. Right? There is a whole speed which is limiting, which is a square root of the length, right? It's basically a combination of g, which is 9.8 meters, and the length of the boat and square root of it, right? So that's it, and that's the maximal that a displacement boat can do without starting to lose energy at the rate which is fourth power of the velocity. Okay,
I have a question for you, which is like, if you can do VMG, velocity made good, faster than the wind, downwind with one boat, could you do it with two boats, which are going opposite each other, tacking opposite each other?
Right. So
and then could you imagine making a frame around them and calling that one craft?
Yeah. So right. So you're referring to the analogy in your video. So you have a very good thing in your video, and then you have this cylindrical Earth analogy. The problem is it has nothing to do with the problem at hand, because the cylindrical wind analogy doesn't have a wheel attached to the ground. So that problem, it's a separate problem. We can discuss it, and we can sign a separate agreement for that one.
but I think what's important is to know that you accept that, right? You accept the idea that these two boats going around a cylindrical hypothetical Earth can go downwind faster than the wind.
Let's discuss that separately. Okay, I don't want to mix up these two discussions, right? These are not equivalent problems.
I'm still confused about something. Because I'm not a sailor, I'm from New York City. I mean, I'm not a sailor. If you do make good on the wind and you have this huge sail, and right at the point where you are at wind speed, the sail goes limp, I presume.
No. So it's a very interesting piece of physics. So it involves more than just sail. It involves also the keel.
But I think maybe his question is, like, we're not going straight downwind. We're always going across the wind. So the sail is never going to go limp because you're never going straight downwind faster. You're always cutting back and forth across it.
So, Neil, this is this mythic thing where the sail becomes an airfoil.
Yeah, I got it.
Yeah.
So
the sailors are just kooky for their freaking airfoils.
So basically what they're saying is that this is the wind. And
hey, what software are you using here?
That's very cool.
Yeah, exactly. So I'm using it's called Squid Ink.
Oh, I've heard of Squid. Yeah.
And I'm using it on this Google Pixel book, of course. So I use it as my primary computer that has Linux and Chrome OS on it, and I also use it to fold it like this and write on it. And also I use it for signing wager agreements. Anyway, so this is so the idea is that this speed, it doesn't know about the wind speed, right? So this speed of the boat knows about the speed that the wind provides onto the boat. So there's a wing here, and so there is some force associated with the sail, and it would take you in the wrong direction if it weren't for the keel, because the keel provides the force in this direction, and the resultant of these forces pushes you in the direction where you want to go. Okay, So that is the idea of close hull sailing. That's called close hull sailing. Okay. Now, since this force and this force don't know about the speed of the wind, they only know about the force with which the wind pushes the sail. You can make it as big as you want by making the sail as big as you want. Right? So this speed is only limited by losses, and as long as you are below the hull speed of the boat, the losses are not so great. And the hull speed of the boat is basically wavelengths, half wavelengths of the biggest wavelengths you can send on the water with your boat. So this is, you just equate that, and the speed of the waves is square root of L over G, right? So that's where that hull speed comes from. It's actually a beautiful piece of physics, and we can talk about that. You should talk about that. Okay, and it also
you get two wakes, right? The bow wake and the stern.
Yeah, exactly. And the same thing applies to swimmers. That's why all those swimmers are all so tall, right? Because and that's why I can never swim fast like this, aside from the fact that my humerus is broken right now. But I can never swim as fast as tall people because the hull speed will stop me. Anyway, so this is going now. Since this velocity is now completely independent of the wind speed and only depends on the wind strength of pulling the sail, you can make it very large, and then you project it with a cosine. All right, so here it is you just project it with the cosine of this theta. And since there's no limit on this speed except for the hull speed, then this speed times cosine may happen to be faster than the wind. Okay, why not, right? So it's possible to have V, cosine theta greater than the speed of the wind. Why not? Okay? There's no law of physics that prevents you that. Your budget may prevent you from doing that. But
okay, so Derek, the lesson here is the Blackbird has to have a hull going into the ground.
So that's
brilliant.
Neil, this is what happened.
Brilliant.
Because this is what made it seem reasonable to me when I saw it 10 years ago, was the torque that the wheels provide. In other words, you're attached to the ground. You're not sliding across an icy lake, and that provides a propeller which has tip speeds way higher than the speed of the wind. But then this mass flow problem, mass flux, it's got to be taken into account. This is really cool. This is what I used to when I had a job. Change is subject to me. I used to work for a living. I just love this.
Just to clarify.
Now let us take if you would, Alex.
Yeah.
Take us across the wind, downwind, on a reach.
Yeah. So okay. So let's get rid of this boat and put the boat. You want to
move the wind? Can you move the wind camera right? And just make things bigger.
Can we move this way?
You mean?
And sort of, I don't know. Is that better for you guys or no? Is
Yeah.
it too big or?
Yeah. That's great. I mean, it's amazing. I gotta get me one of these.
Yeah, absolutely. And you know what's cool about this? I have never encountered a program that works so fast with my writing. So with this pen on any other program, there is a delay. I mean, on the reach.
I think Bill wanted you to draw it going out of reach there.
Yeah, so put some vectors on the bad boy.
Oh, okay. So this sail acts like a wing, right? So the airflow around it creates. So the force here is somewhat like this, okay? And then
it'll be at a right angle to like the quarter chord point of the sail.
It's not the right angle, but it's it's tricky. It depends on the shape of the sail. It depends on how I trim it. It even depends on the boom wang. Whether I tied the boom wang.
There's a component about where the red arrow is going.
Yeah, exactly. And then there is, of course, there is. Okay, if we want to talk physics, there are two additional important things. There is a keel and there is a rudder. So without the rudder, there is so-called. Without the rudder, the boat tends to go into the wind. Okay, so the boat tries to go to the right here. So the rudder has to be in this position. Okay.
Okay.
And so then there are two forces that come from the rudder. Well, from the rudder, sort of this way, and from the keel, sort of. So it's
there's a moment.
Yeah, exactly. Yeah, exactly. So it's complex. So and if you lose either of these elements, if you lose, for example, if you lose the rudder,
you get it so
you're not going to be sailing.
The arrows are both going the same way. We need a couple.
No, but there are different magnitudes. Yeah, exactly.
Yeah.
So
they're different moment arms.
No, but here, no. I got it right. No, look.
Well, the center, okay.
In projection on the y-axis, in projection.
Center of pressure. Yeah.
No, in projection on the y-axis, this force has positive projection, and in projection on the x-axis, it has zero projection. So when you include everything, so here there's this force, fx equals 0, fy not equals 0, and fy compensates for the drag. So that's
okay.
No. I mean, the physics works here, but it's just.
No, just looking.
Yeah.
The moment associated, or the force associated with a keel, and the force associated with a rudder,
Yes.
I have to think about.
Yeah. No, and all three are important. So I'll give you an example. So if you.
Oh, I see. You know what it is? There's a component of the sail lift force.
Yeah.
That's going from our point of view, from the bow toward camera left.
Yeah, that's right. But let me ask you a question. Let me ask you a question.
Green, and I'll be happy.
But let me ask you a question. Okay? I just told you can't sail without the rudder. Can you think of a device that can sail without the rudder?
Well, you just screw with the keel and the shape of the hull and all sorts of things.
No. Windsurfing. Why is windsurfing?
Okay, yeah.
Why is windsurfing?
He's moving his center of mass, or she. He's moving his.
So
center of mass
the brilliant invention that makes windsurfing possible is to make the mast on a tiltable. Okay, so then you can shift the position of the application of the force and the center of mass, and you use that effectively on a windsurf to replace the rudder. So that's the only reason. So if that mast was attached in place and wouldn't move, nobody could windsurf. So that little thing at the bottom of the mast is the invention that makes windsurfing possible. Because otherwise you need a rudder. Otherwise you need a friend, sitting on the back with the rudder.
Or you have to optimize it for only one point of state.
No. It will walk into the wind, and then you need to adjust it. So the angle of the rudder gets constantly adjusted. No, it's actually there are all sorts of instabilities here. It's not that simple.
Now I'm imagining these gentlemen have to go, given the time we have allotted.
This is really cool.
Thank you.
So what is our next step?
Are you going to go back on the flats?
Well, I feel like you guys have given me some marching orders, which is like, we need real-time accelerometer data from the Blackbird. Now,
And more wind speed data, not just somebody standing there with a little...
Sure, 100%.
Which was pretty compelling.
Thank you, but, full disclosure, I think that was the first time they brought out the boat in 2 years, and I think it's in not the finest shape that it's ever been. My hope would be that I can produce a model we can put on a treadmill that doesn't buckle or bow, and Alex can verify the level himself, and he can man the spork if he's concerned about.
Okay, so I'm a theorist.
That's my suggestion.
Okay,
yeah.
I'm a theorist.
Yeah.
I have great admiration for experimental physicists who can actually do this kind of work, but I don't do that kind of work.
Yeah, that's why I'm doing the work. You just come watch.
Right, so I will not be able to verify anything when it comes to experiment. You better find someone who knows what they're talking about.
Well, can you find someone who can be your experiment proxy?
Well, anyone who does this for a living will be fine. But my point is that I'm a theorist and I stand by my equations. So if you have any questions about my solution to this mechanical problem, then please, you know, I'll be happy to answer the question. So
now,
I'm responsible for the solution, not for someone else's experiments.
Now, I want to enter this into the record because it was one of the early things that I proposed to Alex, was that, like, you know, experiments are fun for YouTube, but, you know, between us two physicists, we can do this theoretically. I was convinced that I could show it to you on paper, and you said, I'm not interested unless there's an experiment. I can find the email, right? And so now I feel like you're moving the goalposts on me. Okay. You're saying, like, oh, I want an experiment. I don't want theoretical. And now you're saying, I want theoretical, not an experiment.
So why don't you look up that email? So what? Please, by all means. So in that email exchange, so in its entirety, so what was happening was that, you know, you proposed a bet, and, you know, at first, you know, I don't normally get paid for explaining mechanics problems. Not per problem. I mean, anyway. So I was reluctant to do this, but then I thought, oh, maybe I can do this for Kudu, and that makes it acceptable. And then I said, okay, why not? But then how do we settle a bet, right? So physics is an experimental science, and an experiment would be remarkable. However, I mean, basically, I solve this problem. I can show you the solution. But what if you, in my mind, what if you say, okay, I don't believe equations. I mean, I see what I see. I was in this vehicle, and I don't believe your equations, period. How do we settle that? Well, then I said, maybe I can think of some experiment. And I tried to think of some experiment. And everything that I came up with, I thought was not a reliable test of the phenomenon. Okay?
Well, so you guys take the model to a wind tunnel with a very flat table, properly oriented, where you know the wind speed is constant and this and that. Have the car at one end and see if you can unhook it with an electromagnet or scissors on a fish line or something.
Right.
And see if it walks its way downwind faster than the wind. And Derek, the problem experimentally is going to finding a wind tunnel where it goes real slow.
Well, yeah, and also like a long enough wind tunnel.
Yeah. Hey, there is one. There is one. For the helicopter to fly on Mars, they built this gigantic chamber, and they should go there.
They can't control the wind in there. You can control the air pressure, but it's not a wind tunnel.
But those are the people you want to talk to. But those people can do your experiment, okay?
The University of Washington, you know, where Boeing pays for supports it, they have a couple of big wind tunnels.
Or you just take the damn thing back out on the flats. That's all.
Yeah.
Well, I can call them. We can try to organize it.
And just tell them it looks to you like they got small sample sizes of that effect where the telltale goes slack and the windsock is still extended, and it was only was true for a few seconds.
Right, but I want to reiterate the point that it's somewhat unlikely that any experiment will produce something that will require us to rewrite Newton's laws. Okay.
Well, I will state right here for the record that I believe your analysis to be incorrect. So I think there's a way to poke holes in your analysis. I think there's a way to write.
Would be the first step for
Okay, I think there's a way to write Newton's laws such that we can find a positive thrust on this vehicle at wind speed. A forward force, so that it can accelerate at wind speed and above wind speed.
So this would be a good first step for you.
Okay.
Yeah, so
I can do that.
Just for me, sitting here the last hour, here's W, here's lowercase u, here's lowercase v, here's uppercase v, here's capital T, here's capital F sub T. There was a lot going on there.
So before I share these slides. Before I share,
I'm dookie for an ADA.
Yeah. So before I share my slides, I will clean them up and use the notation from that paper.
Well, use the notation that you feel is clearest. And for me, velocity is v or u. I mean, getting the W velocity looks like.
Well, that's what they use. That's what they used. Okay, fine. I will change. Okay,
do it the way you are most comfortable.
Listen, I can use any notation. Notation doesn't matter.
Looking at your derivations, it doesn't matter that you were using the same symbols that somebody else used in a website that no one is going to look at. So that's my first. Second, Derek, I just want to make it clear to whoever will be watching this that no one assembled here is thinking we are violating Newton's laws.
Yeah.
And even Alex's presentation is set up, constructed, following Newton's laws and all other that we know about movement and momentum and conservation of
Energy.
energy and mass, all of that, that's fine. If your analysis is wrong, Alex, it's not because Newton's laws have failed, it's because there's some term that has been neglected that needed to be added to your analysis. I just want to make that clear so no one thinks that Derek is just going to try to find a loophole in Newton's laws, because that's not what he's trying.
Perpetual motion and so on.
Right.
So my question, what started me thinking about this years ago, was the tip speed of the propeller. Because propellers have all sorts of subtle issues that I wondered about. And I'm charmed and intrigued by Alex's assertion, offhandedly during this recording, that the cylindrical two sailboats going down faster than the wind is a separate problem. I'm intrigued by that. So for me, the question is in the propeller, but Alex's analysis is pretty compelling.
Yeah. So
Another
right. So since
aspect that I'm going to want to look at was energy per unit time power. Was there a factor missing? Was there a 1/2 missing early on that appeared later? I don't think so, but it was going fast in notation that was unfamiliar to me. So I'm excited.
So I'm going to
taking this on. This is just cool as heck.
yeah.
Hey, Derek, I got to run.
Okay.
You have enough of us to put something together on that?
I have a ton. So thank you guys for being so generous with your time and for joining us and for witnessing this today.
You got me going, because I saw these guys years ago at Google and everybody loved them and thought they were geniuses, and I was like, well, that's pretty cool. And as I say, there was a boat, or maybe more than one boat in Seattle, where some eccentric guy had rigged up a propeller above the water and a propeller below the water. And my understanding by these guys I went to go look at boats at lunchtime with was, oh yeah, you can do that, but you know it's a huge thing, and you can't go anywhere but downwind. And so
no. If you could do this,
I never questioned it.
No. That there is market for that. There are many boats crossing the Atlantic and the Pacific, going downwind along the trade winds. Okay, so if there was some contraption that you could put on a boat and make it more comfortable going downwind, that would be very, very welcome. In fact, I know a sailor who redesigned his rigging specifically to go across the Atlantic with his own design. Okay, because he would want to go wing in wing. It's when you have two sails, kind of on opposite side, and you're going straight downwind. So I guess I'm not supposed to tell about it's his invention. But anyway, so he redesigned the rigging so that it would make it easier, specifically for crossing the Atlantic. So if there is some propeller that you can put on the boat and dip something in the water and it will help you go downwind, people will buy it. So there's a
market.
There is market for you.
I like
Absolutely.
it.
So I consider myself a formal skeptic. I'm in both skeptic organizations, and I love this problem. I accepted it 10 years ago without really much thinking about it, and so I'm ready to play. I think this is fantastic. This is going to enlighten the world.
Great.
And Alex, a delight to meet you.
Very nice to meet you, Neil.
I really made you.
Very nice to meet you.
Hey, let me ask you, do you know Charles Williamson?
I don't know.
Yeah, anyway.
I don't.
I got to run.
Okay. Thank you, Neil. Thank you very much.
Thanks, guys. Thanks, Neil.
Guys.
Cool. Carry on.
All right.